bits in a register is known. What's the maximum integer? What's the minimum integer? What's the expression for -1 in binary or hex? And again, the old problem of converting between these two. Converting between the decimal expression and the hex expression. It's in quick, if you're presented with a negative number, let's see, is that, no, what would you do? I would compute the positive hex and then apply that rule, flip all the bits and add 1, and then you'll have the negative hex. Let's do that again. If you're given -37, find the expression for 37 in hex or in binary. Flip all the bits, add 1, and you'll have the expression for this one. First time we ought to do one of those at the end of this review. Okay, signed integers. Okay, see if I wrote this right. The third group of numbers are the most complex. They're IEEE numbers. Okay. We've only studied IEEE in 64 bits. There are IEEE rules for 32 bits floats, but we'll do it after the midterm. Okay. So the bias number fits only, that we know, only fits 64-bit floats. 32 bits have a different bias number, and we'll study that some other day. So you should know bias number. And the base number. Base number is the exponent of the smallest positive normal number exponent. It's a hidden number. It's -122 for the 64-bit case. Whereas bias number is +123, 1023. You should know how to recognize subnormal numbers, how to convert those subnormal numbers to from decimal to binary, or even better is float, is binary. The hex expression is easier for us humans to read and understand than 64 binary bits. So conversion that I prefer most of the time is between decimal expression and a hex expression. Okay, here's a practice problem. More math. There's gaps between numbers, and how far apart are those two numbers? And a given float and its next highest neighbor, for instance. We can measure the gap, and it keeps changing depending where you are on the number line. Here was a question: how many float numbers exist between 1.0 and 2.0? So, yeah, you have to take into account the size of the mantissa, 52 bits. In the mantissa, there's every possible combination of 1 and 0 and among 52. So there's 2 to the 52 numbers. If you hold the stored exponent constant, but what's the stored exponent between here and here? I think it's only one number. Oh, between 1 and 2, I'm sure the stored exponent is only a single value. It doesn't change. And so this would be the number of numbers between 1 and 2. Now, if you move over to 2 and 3, it's not the same anymore. There's a different, it changed. Okay. ALU add. Okay, the ALU does arithmetic for us. But that's using ALU is fine for a business major, but it's not good enough for a computer science major. We want to know, how does it do it? So how do you add, I don't know, where's my blue one? How do you add two float numbers? Uh, in base 10, 7.834 times 10 to the 5 plus 6.119 times 10 to the 1. To make that addition happen, these two have to agree. One of the two numbers has to be modified so that the two exponential terms are the same. Then you can go over to this side and start adding. Okay. That's what it means by how does the ALU actually add two floats. It has to do that trick right there. And then the next one is, what happens if you add a very large number and a very small number? Here it is. First that one, period. And then what happens when you add a large IEEE number and a small IEEE number? The answer is usually wrong, mathematically wrong. Uh, how can I show that? Oh, yeah. It's in binary. Suppose you have 1 point. To somewhere plus -4. Okay. There's a long distance between those. There's a big gap. And mathematically, you can add these on paper and it comes out with the correct answer. But in a IEEE 754 computer system, it'll be wrong. That produces, it's going to lose data, especially on this part of the small number. Uh, produces wrong answer. Okay. Now, to make this addition happen, we have to accommodate one of these two has to change so that it matches the other one. And you accommodate it by shifting as this number increases, this one has to slide the dot towards the left and it becomes a smaller number. So adding a large number and a small number, typically, if it's too far apart, typically fails. I had an assignment a few years ago where students were supposed to add this sequence where n went to 1 trillion. The problem is when 1 over 1 trillion is so small that it's being added to this accumulated value up to that point that it's losing part of the data of the last of that small number. And so after many additions, the error accumulates larger and larger. And so it was numerically wrong answer. Okay, so as an experiment, some people did it in reverse. 1 over 1 trillion plus dot, 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 plus 1/3 plus 1/2 plus 1. And the same set of numbers, but they don't match. This answer is not equal to answer B. Because of the error problem of holding in the same register large numbers and small numbers. It just doesn't work. All right. Let's go on. What is here? Oh, here's it. I was doing that same discussion. Here it is written backwards from 1 trillion downward to 1. And you add them up and you get a different answer. Okay. All right. You know what NANs are, how to identify a NAN, and where they're located, and the defining property, and plus infinity and minus infinity are special cases of NANs. Be able to do conversions between a decimal float number and an IEEE float number. Okay. Some of them, this is a tricky one. 404 A. There's nothing wrong with the stored exponent. That's a nice number. But the mantissa looks like hidden bit 1010101010101010. Okay. We have to use a formula to add, these are powers of 1/2, to add powers of 1/2. And if there's time, I'll do one of those at the end of this discussion. Okay. This is an easy float. The stored exponent is right there in front of us. The mantissa has an 8 hidden bit, and the 8 number, that's all there is. The rest all zeros out, times 2 raised to the stored exponent. Stored exponent on 4.402 is a 3. That's it. What would that be? If I multiply by, if I shift the dot by 1, it says 1, and then this is times 2 to the 2, compensating for it, which is 3 times 4, which is 12. I get that under the machine. I just solved this one here. That's a nice, pretty IEEE number. The bias number is 3FF. There's a distance of 3 between 3FF and this one. So the stored exponent is 3. The hidden bit is 1. The 8 has a leading 1 and all zeros. So it looks like that. And shifting the dot, it looks like 11 times 2 squared, which is 11 is 3. 2 squared is 4, which is 12. I should make it show up as a float 12. 12.0. Okay. Don't be surprised that there's questions about our programming language. Okay. Most of these questions are write a block that will accomplish a little task. So here's one example. Write a block of x86 that, here it comes, inputs 2 floats with 1 call to scanf. There's many other little exercises like this. You just write the block into the test document, and that's it. So look at some old tests. You'll see little blocks questions that were used in the past. They're good practice questions. I never lectured about licenses yet, so that question is not on this test. It is on the sample test questions, but you won't be faced with it. There, let's try to get it under the camera. No question on licenses. Okay. Everyone still with us? Integer instructions. These are on the special list of approved, recommended assembly instructions. That word is instructions. Okay. Now, this weekend, or if you go to SI meeting and you're going to practice this, it follows the rule of ordinary math. How can I write this? I want to do it in black if I have black. Oh, black. Okay. I started to explain it here. When you multiply two integers, an x integer times a y integer, if this has like 5 decimal places in it, and this has 4 decimal places, you can expect 9 decimal places over here. 5 digits and 4 digits multiplied together, you usually get 9 digits over here. In bits, it's the same story. The computer has to deal with this. So X is a 64-bit integer. Y is a 64-bit integer. And Z is their product times Y. Okay, there it is. Z will have 128 bits. Okay. And that makes a problem for the multiplication action on integers. Watch what it does. It generally will put it in a split register, RDX with RAX. And it's a big number, big integer number, but the 64 lower bits are here and the 64 higher bits are here. Okay. Now, that complicates life with division. If we're going to do a division, then X equals Z divided by Y. Okay. I'm using this and divide both sides by Y. So here 64, and this is 64, and then 128. To make division, either one of these, the signed version of division or I got it backwards, the unsigned version or the signed version still needs that your numerator have twice as many bits as the denominator. But how do you get there? How do you make that happen? And that's where the role of register extensions comes into play. Extensions. Okay, so if we want to divide 123 by 37, we need to put 123 somewhere. Move whoops, 123.
You slide the paper.
Yes. 1 RBX 37. And if you said this would be wrong, these are unsigned, so I'll use the unsigned division. DIV RAX by RBX. That'll give you a wrong answer because the numerator is not 128 bits. So there's a command. Here it is. It's called CQO. It takes no operands. Operands. But it will take this numerator, RAX, and extend it numerically over 2 registers. So RAX turns into RDX AX. Okay. Uh, the numerator has, we got to see it. I recommend you look at it in the, I gave the page number, by the way, in that new upgrade to the list of instructions. Look at how he does it. He calls this one and then it puts it over two registers. There's your 128 bits, and then the division works. Okay. So in the list of approved instructions, I added, I think it at the end, the list of extensions. The extensions are not there just for, a game playing or fun. They actually serve a serious purpose. Uh, let me try here. I can remember some. Oh, in fact, I had a, where's my handwritten note? I think we have time to do this. What's the clock say? Yeah, we have time. Okay. Here's some that you should look up. CBW. It's in Jorgensen, page 79. This will extend an 8-bit register to a 16-bit register. CWDE, an 16-bit register to a 32-bit register. What's it called? CDQE, a 32-bit register to a 64. And CQO extends RAX into a pair, because we don't have a 128-bit register, so they have to use two to hold the result. Okay. And the extension doesn't mean just paste a bunch of zeros on the left side. It has to account for the sign. If the sign of the number in RAX is negative, there's a lot of ones, and then you come to the actual number. So these take care of that. Uh, there's a list on page 79 that show these, and you'll need them if there's anything to do, if you have to do something with multiply two integers or divide one integer by another. The list goes on. These, I don't know why there isn't a little e here, but there isn't. This little e says extended internally. AX is inside of EAX already, extended there. This says extended internally from EAX to here. This one can't extend internally because there's no enclosing bigger register that holds it. So in programming, we often find these strange pairs. I'll do this and then we move on. CWD, no operands. What it does is it takes a word, AX, and extends it to DX, AX. There's no E on the end of this. See, the E up here is different. CD, what's the next one? CDQ. I'm reading the wrong place. CD, that is right, CDQ. It takes EAX and extends it to EDX EAX. Yeah, that's what it does. So you get a 64-bit number out of this 32-bit one, but it's split 32 and 32. Now, it's like this one without the little E on the end. And then the last one, we can't put an E on the end because we don't have a register big enough. This one takes ERAX and it sends it to a split RDX RAX. And that's good for division of by a 64-bit integer, because this is 128 here. Okay. It satisfies the need of div. Div is used if both operands are unsigned. And it's idiv if one or more of them are signed. Two's complement. Okay. I did a brief development there. This all in this. See if that all fits. I think the author's description is more detailed, but that's what's happening. Okay. Let's go on to the next one. So put this here. Okay, so I was showing examples why this is required. Division is the reverse of multiplication. Multiplication adds bits. 64 bits times 64 bits is 128. Division has to be 128 bits divided by 64. Even if your number is not big enough to need 128, it's still going to use 128. So the extension instruction comes into play at that point. Now let's look at the next one. Oh, this is more of the same. Extension, here it is again. From 32 to 64, and then the 64 is divided. Oh, you're trying to do this, but it doesn't work. You have to get the numerator to become 128 before this division will be mathematically correct. And that's where this extension comes into play right there. It precedes the division, one's instruction before it. Okay. Let's see if I wonder this. Okay. What is that? Can we interpret that? Convert a word to a double. That's a 16-bit to a 32. Convert a double to a quad. That's from 32 bits to 64 bits. And this one, you ought to read this one too. S is for single number. X, no. It isn't, in this case, it's not. This is for sign preservation. Preserve the sign and convert the source going to the destination. X is for extension into, why is it double? I lost that one. It would be move S X D This is what I think it is. I'm pretty sure it is. RAX EAX. a 32, that's the double. Why isn't the destination shown here? But S is to preserve the sign, and X is extend, and D is the starting register. Over here is a double. And the destination, it's not part of the instruction name, but you'll get an extended value here. So the author made a special little paragraph about this one unusual instruction, one unusual move statement. It moves and extends in the same statement. Okay. How about here? My other camera. You should know about von Neumann. Uh, he was in his time period. If you read about it, he was a famous scientist in the early 1950s. Um, did a lot of unusual math. Traveled on a Navy ship to Bikini Island when they blew off an atomic bomb, and the radiation covered the Navy there. The guy was present. He was doing amazing things. Big Indian and Little Indian. You should know what that's all about. A business major uses computers for all kinds of purposes, but they don't know what this means. A computer science major knows the inside workings. We need to know what is MSB and LSB. Those are bytes, the largest, the most significant, and the least significant. I think I mentioned NANds earlier. Organization of memory. There's a nice diagram in your book around page 17 or 19 that shows the relative location of operating system, executable code, BSS data, data, um, gap space, shell, stack space. Now, it's a very abstract diagram, but it serves its purpose. It assumes a one core processor, which we really don't have anymore, but it still tells a good story of how memory is organized while the machine's running. Okay, RSH. You should know what those commands inside of RSH are doing. What is ELF64? What does the hyphen mean in front of some things? And what does the .o imply in some shell commands? Uh, each line inside the bash file is a shell command by itself. I lectured on heroes sort of at random times. Heroes are the people who built this science that we're living today. Um, who was first? I guess Babbage was first. Now, the experts today still refer to his computer as a computer, even though it didn't have any electricity. But it is recognized by experts that that is the first computer. So it started with him, and then of course Ada was the main programmer for that computer. And the heroes continue until some of them are still alive. Torvalds is still alive. He's living proof that he's part of living proof that building an operating system is the hardest software project on earth. There are only three alive today. I think there's three: Windows and Linux and BSD. And then there's some derivatives out of those. But a country's government The United States government does not build an operating system for use by the CIA. No country ever did that. Only three operating systems still survive today. Uh, and that's all there are. It's a hard project. So Torvalds found the solution. Let the rest of the world build it, and I'll just manage it. And everybody else does the programming and submits their code to me. I'll check it out and then put it in the operating system. He built a big operating system using volunteer labor. Microsoft has 500 highly paid engineers building Windows 12, and they work on it for several years, and it's still released with some bugs. And Torvalds get some bad code escapes through, but the volunteers search it out. That's amazing protocol. It's amazing technique of building big software. Just let everybody else build it for me. Who is the holy saint of assembly programming? Chris who? Yeah, Chris. What was his last name? Tor Sawyer. Um, that's that program should be, maybe it already is, in the Guinness's Book of Records. That is never going to be done again in assembly language. Uh, Humans don't take that much time, 3 years out of their lifespan to make one program. Uh, but he did in the 2000 era. And Roller Coaster Tycoon is still sold on eBay, but he doesn't have rights in it anymore. I think last I know, he's sold it. So this guy's still alive. He has a website, and he built a game program all in an x86 assembly website. Incredible feat that nobody else will ever do. I predict 100 years will go by, nobody will repeat that. Who is the He's not the founder. He just did an amazing thing. Who is the founder of assembly programming? I guess you could ask ChatGPT. Who's the founder of all assembly? Someone had to be there at the very beginning and do it first. And that was Kathleen. You're right. Founders. You know how to find your last name. Okay. Uh, is she American, British, French, or Canadian? Is she dead or alive? She's dead since about a year ago and lived much of her life in Canada, but she's British. Okay, she died in Canada. So let's see. Who? Some of these are still alive. Grace Hopper, uh, first programmer on a viable computer in the United States. This is not during World War II. The British were trying to crack codes, but a viable computer in the United States was the Mark I at Harvard. She was not the director of the project, but probably the one and only programmer on that computer. Not that person, Grace. APEO, Hopper. Okay. Dead, this is dead person. Sawyer's alive, Kathleen's dead. And who networked two computers together for the first time? Laid the foundation for TCP/IP. First network was? Nobody knows here. And you want to make big salaries on the shoulders of other people, and you don't know who they are. First network. Computer. That experiment later turned into the internet, which is not the web, it's the first computer. Okay, you go look up who this is, and he had a sidekick who seemed to do all the lab work, whereas the manager here got all the publicity. It's a funny story, but Bob Kahn did all the work, but somebody else got the credit for it. He's alive, and I don't know about Kahn. This guy's alive, and Berners-Lee is alive. Looks very old in pictures now. He looks as old as me. That's really bad. So, okay, so you get all 25 names down so that I can ask you any one of them, and you'll be on your list right there. That's why we have open note tests, so you don't have to look it up. You don't have to memorize it. What else is on here? Heroes. Uh, Calling a function has a lot of overhead. A lot of stuff has to happen internally to make a function call. But in a macro call, that's not true. Macros don't have that overhead. Uh, but I haven't lectured fully on this, so this will either be nothing or some minimal thing. Does it cost the computer machine cycles to call a function? Yeah, quite a few of them. Uh, so you need this is a number. Assembly, that's a number. That so five, which one did I use? 5, arrow, 13. You can say move RAX, comma 5, arrow, 13. What number do you get? What you get is 5 times 2 to the 13 as an integer. And I don't know, it's a notation for programming because it's hard to, like, why is it hard to raise to the 13? They didn't want to do this. That's what it is, and that's what it is. But I don't know. This is maybe easy for, I don't know why it's that way. Okay. But that's what the symbolism, two leftward arrows, what it means. And we're not out of time, I hope. We're right on 11 o'clock. What was this about? Oh, among the instructions that are very useful is shifting to the right and shifting to the left. And here's an example of how you would write it. Shift right on the register RBP 5 bits. That's what it means. And if this is the starting register, RBP, or say P, RBX, if RBX is this one, and you shift right 5 bits, then these 3 have moved to here, 5 spaces, and the fill-in is always with zeros. Here's going in the opposite direction. There it says go, what are we going to save? These two are going to be lost. Lost. And the rest move over uh, 2 places. And then there's zeros are always to fill in. Not in the sense of in these two instructions, shift left and shift right, zeros are always to fill in. So why is that important? It's for timing, for fast timing. In industry, assembly is used to make things fast. Well, let's summarize it here. If you shift, I already have the summary here. Shifting right, let's see, shift right, RCX 3 is the same as RCX divided by 2 to the 3. Okay. Integer division, where you lose the remainder. You don't. Okay. So shifting right is a division by 2 raised to the number of bits you've shifted. And shifting left is a multiplication. Means RCX times 2 to the 4. Okay, so in computer science, we use 2 raised to some power all over the place. You just find it in many places. And it's very frequently the case you need to multiply by 2 to a power. Someone benchmarked it, and found that these multiply and divide faster than ordinary multiply and divide. So this is a fast division, and this is a fast multiplication. I think we have that in base 10, don't we? I think we do. 3, 4, 9, 7, 6, 5. Okay. And you want to, the bases, you want to divide by a power of 10. Divide by 10 to the 3. Okay. What you end up with is the dot moves over here and you throw away this part and you're left with 349. 3, 4, 9, 7, 6, 5 divided by 10 to the 3 is 349. That's what's happening back here, but it's just 10 is replaced by a 2. We're dividing by this guy here, 2 to the 3. And how about multiplication by a power of 10? 3, 4, 9, 7, 6, 1 times 10 to the 4. You shift it to the left and add some zeros. 3, 4, 9, 7, 6, 1, 0, 0, 0, 0. And your multiplication is done. Okay. So we have it in base. We have that same effect in base 10. Okay. Did I get that under there? Where's that? Okay. I think we're done for today. There's we talked about that already. And concept test that I've been talking about, where you'll see it on Wednesday at class time. Be at your computer, and I'll send it to you, hopefully, pretty much, yes, at about 9:55. on Wednesday. And you sent it back to me by 12:00. I mean, I don't count to the minute. If you were up to 3 minutes late, 4 minutes late, you're still okay. If you're 22 minutes late, uh, no, you're not okay. So there's the due time. What's important about those? Oh, yeah. Don't convert it to PDF. Acceptable. We don't have a, this is our last chance to be together before the test. Acceptable are dot ODT dot DOC dot DOCX. I can, on those formats, I can easily use an ordinary word processor and put little comments next to your answers. With a PDF, I have to get out a special PDF editor to make a comment in it. And it got so tedious, I just say, I'm not going to deal with PDFs anymore. Don't send PDFs. Don't send JPEGs that are pictures of your test. Don't send video of you writing on your test paper. All those other formats don't count. It has to be these. Let's see, is there anything else that we need to go over? I can't think of anything right now. Any questions, anybody? Yes, Joanna, you got it right. I don't know. I think Vin is abbreviation. I think it's Vincent or Vinton, but just like William gets abbreviated to Bill, Vint is his short name. That guy had two primitive computers and was thinking about how can we get the data from one to the other. There should be some way that we can do this. So he had to create, it was not just plug in two USB cables. It was, he had to create the protocol for packet switching. And that which we now know as TCP and IP, that is two of these protocols. So he had to create that and then try it out. And sure enough, on the second computer, there arrived he sent a data string. There it arrived. And it was the first transmission between two computers. And from that, they added three computers together, and then six computers together, and then dozens of computers together. Before you knew it, there was the internet. Uh, Now that predates, don't confuse that with the web. There was an internet with no web. Okay. People were sending email and transmitting full documents long before there was a web. You couldn't see any pictures then, obviously, but email was flying all over the country since 1970 to, when did this web come? 1990. And they were experiencing viruses and all this stuff was happening, but there was no web. Tim had to take the existing internet with all of its email traffic and put a graphical interface to it. And then that became the web. This is Tim Berners' accomplishment, is to make it a graphical internet. Okay. So the question of who invented the internet is not Tim Berners-Lee. It's Vinton or Cerf. Okay. All right. Did I'm missing something here? Hmm. Okay. Well, everyone, I'm done. We're done. That was our review session. There's nothing on this test about software licenses, and there's very minimal, maybe nothing about function calling. Function calling results in a bunch of internal pushes and they have to move the RBP register to the front of the stack, and the stack then moves forward. RSP moves forward. But that's not on this test. Function calling is a different bag. Have a great day, everyone. Keep on working to finish assignment 3, due Monday or Tuesday of next week. I don't have the exact date. Okay.
I'll let you know when I get my score. That's the count though. Yes, but it doesn't use it. Yeah, so it said that count 2 is a requirement, but the professor said that it's not needed. So you might be able to get like an exception.
All right.
For assignment 3, you use the physical file when you submit through console.
Yeah, I took all the way up to 3.
Like, what was your last?
For assignment 3, we have to verify the inputs.
Yeah.
And then I was finding
Yeah.
same thing we did last assignment.
Yeah, it's about the same thing. Use this float.
And then we
Wait,
also
do I
turn it
remember
in
how?
with the
Oh, yeah, submit it too.
to submit it to. Okay.
Right.
Because
We have,
I wasn't sure if like we're not allowed to submit it because it's not under the required.
oh, didn't I mention it clearly in the
Yeah.
description?
It didn't say exactly to
I
use
think
the
there's like
physical
the actual
file,
like.
but
Oh,
in the picture
Way
part
it's
too,
tested,
it doesn't
so.
show it inside the.
that's my mistake.
Yeah.
You should use it.
Oh,
Yeah, I'm giving you my permission right
It's
now.
like,
got it. Yeah, I double checking that I could submit that also.
Right, submit it with the other file.
Thank you.
Professor, can I take pictures of all your?
Sure, let's, upside down right now, but you can take all these.
Yeah. Thank you.
Just go there.
Yeah. I just have this stuff.
I have
Already.
programs to say.
So I feel like I can do them sometimes, but then I'll look at like other ones, so I'm like, all
What other?
Oh, no, we have
You,
the.
oh, you have other, notes.
Yeah.
Okay,
We're just combine these.
okay,
Thank you.
you're welcome.
Kept it in order.
Okay, thanks. Keep it moving. Hi. Oh, well, I'll give my best effort.
So I think I finished it, but is this okay for error case handlers where I just check it immediately and if it's invalid, I
Oh.
don't let them enter it?
Yeah, no, I'm okay with that.
Okay.
It's not the one I demonstrated, but I like that too.
And then if it's not a triangle, I just, I just kill it.
Yeah, that's good too.
Okay,
That's
so
okay.
let's just go okay to turn in.
It's okay for me.
You can.
Okay. Okay. Okay.
No, I.
What are you doing?
Fine.